The design of a bridge starts with identifying its geometry suitable to the given situation. Check how to draw the geometry and identify the shear and moment for the design here in bridge engineering. We are given the task to identify the preliminaries for a simply supported highway bridge carrying two traffic lanes across an 18-meter river width. The two traffic lanes have a width of 8.4 meters, and there are 0.8-meter width sidewalks on both edges, also situating the crash barriers of 0.3 by 1 meter size. The wearing surface will have the future wearing coat integrated, thus it turned as 80 millimeters. The girders we consider are ASHTO pre-stressed eye girders. For the unit weights, use 24 kN per cubic meter for reinforced concrete and 22 for asphalt. The geometry of the bridge starts with the bridge length. There are two approaches to use where the greater value will be adopted. Before starting, be reminded that the first equation is in English units, so do the necessary conversions. The first equation uses the skew factor. L is the bridge span, and H is the height of the columns. And taking the conservative approach, we use L upon 12. That makes 18 meters converted into feet upon 12, giving 4.92 feet. The skew factor for straight bridges is 1. We assume a straight bridge as there isn't any data of the alignment of the bridge, and having a short span, we can assume a straight bridge just the same. So we compute for the edge allowance as 8 plus 0.02 of the converted length plus 0.08 of h, then multiplied by 1 as the skew factor. We get 9.5744 inches, or 0.243 meters, rounded to 25 centimeters. The other equation is shorter, only needing L, and we get to solve N as 0.06 of 18,000 millimeters plus 100 mm, giving 1,180 millimeters. This is obviously greater than the first figure, so we adopt this and compute for the total bridge length as the clear span plus twice of the end allowances. That turns into 18 plus twice of 1.18, giving 20.36, rounded to 20.5 meters. After identifying the length, we move about the determination of the other parameters, starting with the thickness of the deck, where we are required to look for the girder span first. As shown from the previous videos, the procedure will somehow be an iteration, where we start by assuming a value for S guided by the bridge material. Since the girder is pre-stressed, we assume S as 2.5 meters, then proceed with the slab thickness computation from the table. T is then 1.2 of 2,500 plus 3,000 all upon 30, which gives 220 mm. From here, we can determine the number of girders using the total bridge width, that is clear road width of 8.4 meters plus twice the width of the sidewalks, where we get 10 meters. The number of girders is taken from the total width of 10 meters divided by 2.5 meters, then add 1, so we have 5 girders. Knowing the number of girders, we continue with their actual spacing. We have 10 meters over 5 less 1 girders, where we get 2.5 meters. The actual spacing is the same as the assumed spacing, so no need for any iteration at this point. We then have the concrete deck thickness of 220 millimeters, with 5 girders spaced at 2.5 meters. To take the total deck thickness, we also incorporate the wearing coat, giving the total deck thickness of 300 millimeters. Next is to determine the depth of the girder. We know that PSCI girders are to be used. With the span to depth ratio provided, we focus on pre-stressed concrete having the ratio of 18 to 25. The girder depth is then assumed as the length divided by the ratio of 25, and we arrive at 0.82 meters depth. For the proportion girder depth, check the eye girders from AASHTO. 820 millimeters is closest to 914, the depth of type 2, so we use this girder. This concludes the bridge geometry. Having to know the size of the bridge, we can analyze the loads. We are to take the interior girder as it is where we can look for the maximum loading. The tributary width for interior girders is 2.5 meters, and it would also be good to know that exterior girders have an effective width of half or 1.25 meters. From the top, we compute for the load due to the wearing coat, that is a thickness of 80 mm applied on the tributary width of 2.5, then multiply the unit weight to get 4.4 kilonewtons per meter. For the deck, we take the thickness of 220 mm times the width of 2.5 meters, then the unit weight of 24 kilonewtons per cubic meter, giving 13.2 kilonewtons per meter. From the AASHTO girders table, we can draw type 2 as an eye girder with depth of 914 mm and top and bottom flange widths of 305 millimeters. These are the parameters we need for now. There is stay-in-place forms for the concrete deck, and considering a unit weight of 5 pounds per square foot converted into kilonewtons per square meter, we multiply the remaining deck length, that is 2.5, less the top flange width of 305 millimeters, and get 0.53 kilonewtons per meter. From both ends are the sidewalks, taking the standard depth of 6 inches. We can then compute the added load as two sides multiplied by the thickness of 0.15 meters with the width of 0.8 meters, then concrete unit weight. Then all these will be shared by the 5 girders, so we get 1.15 kilonewtons per meter. Next are the barriers. There are two lines with a given size of 0.3 by 1 meter, multiplied by the concrete unit weight and divided by 5 to have 2.88 kilonewtons per meter. The dead load brought by the girder is seen from the table, and it is 384 pounds per foot, converted into kilonewtons per meter, resulting to 5.61. We place a standard hunch for each girder, and that would be 1 inch multiplied by the top flange width, then concrete unit weight, and have 0.19 kilonewton per meter. Although the figures have already been rounded up, it would be safe to add a dead load of 0.02 kip per foot for other bridge amenities like the lightings and the railings. This is taken as 0.03 kilonewtons per meter. Take the summation of the loads on the deck and arrive at 23.59 kilonewtons per meter. With the dead loads identified, we take the raw shear and moment due to dead loads. Shear and moments are taken at the midspan of the bridge. Thus, maximum shear is the load times the bridge span over 2, and the maximum moment is WL squared over 8. With dW computed as 4.4 kilonewtons per meter, the shear is then 45.1 kilonewtons, and the moment is 231.14 kilonewtons per meter. For the dead load on the deck component, the shear turns out as 241.8 kilonewtons, and the moment is 1,239.21 kilonewtons meter. After the dead load is the live load. There are 3 parameters taken into account. Those are the design track, design tandem, and the design lane. Since the design track has 3 axles, we use the closest axle spacing of 4.3 meters from the rear. To have the maximum shear, we locate our loads at the supports, placing the design track in this location. Like the track is entering the bridge, place the rear axle at the left support. We then take the reaction at the first abutment, and that is through summation of moments about the second abutment. This reaction provides the shear and is computed as 1 upon 20.5 times the load of 145 with a distance of 20.5 plus the other 145 times the distance of the bridge length less 4.3. Then add the front axle load of 35 with a distance of 20.5 less 8.6. This is simplified as 279.9 kilonewtons. Next is using the design tandem. The design tandem has two wheels spaced at 1.2 meters. Each wheel carries 110 kilonewtons. We also place these on the support for maximum shear, and we compute the reaction as 1 upon 20.5 multiplied by the left wheel times the distance of 20.5 plus the right wheel with a distance of 20.50 less 1.2 meters. The reaction is solved as 219.94 kilonewtons. Comparing these two shear values, that produced by the design track governs. The last parameter is the design lane. This is the distributed load of 0.64 kip per foot converted as 9.34 kilonewtons per meter throughout the entire span. Again, take the reaction, but this time we can use WL over 2, or 9.34 times 20.5 all over 2, giving 95.735 kilonewtons. The shear per lane multiplies the greater value from the design track or tandem by an impact factor. The total shear is then 279.9 multiplied by 1 plus 33%, then add the design lane shear of 95.735 to have 468 kilonewtons. Now let's solve for the moment. We start by looking for the centroid of each design vehicle. For the design truck having 3 axles, we look for the centroid by using the summation of moments over the summation of forces. With training from statics, you can already deduce that the resultant of forces will be found between the two rear axles. That is where the centroid is. The summation of loads is 145 with another 145 plus 35, or 325 kilonewtons. Using the reference for bar X at the front axle, we take moments about this point and get 145 times 4.3 and another 145 times 8.6, or that is 1,870.5 kilonewton meter. We solve for bar X now, and that is 1,870 divided by 325 and get 5.75 meters from the front axle. After identifying the centroid, we can then take the maximum moment when we place the design track near the center line of the bridge. That is exactly at the location between the centroid of the design track and the middle axle. With bar X computed as 5.75 and knowing the distance of axles as 4.3, we can compute for the distance of the loads on the center line, and that is half of 5.75 minus 4.3. or 0.725 meters. Next is to take the reactions. To simplify and shorten their computation, we can use the resultant load. With moments taken from the abutment 2, we have the reaction on the first abutment as 1 over 2050 multiplied by the load of 325 times the distance of 10.25 plus 0.725. And this gives 173.99 kilonewtons. The right support reaction is taken as 1 over 20.5 multiplied by the load times 10.25 minus 0.725, resulting to 151.01 kilonewtons. Now solve for the maximum moment by taking it from the middle axle. The maximum moment includes the lighter load where we take the reaction of 151.01 multiplied by the distance, 10.25 less 0.725. Then subtract the load with its distance of 4.3. The maximum moment for the design track is 1,287.87 kilonewton meter. For the design tandem, having only two axles, the centroid is at the center. Then again place the design tandem on the bridge, having the center line divide the distance between the centroid and one of the axles. This gives a distance of 0.6 meter. The left reaction is then 1 over 20.5 times 220 times the distance of 10.25 plus 0.6, which is simplified as 103.56 kilonewton. The right support takes 1 over 20.5 times 220 times 10.5 plus 0.6, and this is 116.44 kilonewtons. With similar setup as the design track, take moments about the axle and have the maximum moment as the reaction of 116.44 multiplied by the moment arm of 10.25 less the quantity of 4.3 minus 0.60. You will get 762.68 kilonewton meter for the maximum moment using design tandem. This is much lesser than the design track, so we use 1,287.87. Next is the moment from the design lane. For the uniformly distributed load, we take the moment by WL squared upon 8, or 9.34 times the square of 20.50 all over 8, and get 490.64 kilonewton meter. At last, the raw moment is computed as the bigger moment from the design track or tandem, multiplied by an impact factor, then the design lane. In this example, we have 1,287.87 times 1.33 plus 490.64 and get 2,203.51 kilonewton meter. One portion is completed as we have figured out the shear moment of the bridge. The next thing to consider is how much each of the interior girders carry, and this is done using the distribution factor. Using two or more lanes loaded, we first identify the moment carried by an interior girder. This is using the empirical formula provided by AASHTO as shown. We already know S as 2,500 millimeters. L is 20,500. The deck thickness as 300 mm. But we are to figure out K of G, which is N times I plus A multiplied by E sub G squared. The first parameter N is the modular ratio, where from the equation uses the modulus of elasticity E. Since no moduli is given, we solve N using strength. The strength of standard concrete mix for bridges is 28 megapascal, and the strength of standard pre-stressed concrete is 41. N is taken as 41 over 28, giving 1.46 rounded to 1.5. For type 2 AASHTO girder, the area is already provided as 369 square inches converted into square millimeters, giving 238,064.04 square millimeters. The moment of inertia is also given, and it is converted into 2.122 times 10 raised to 10 millimeters raised to 4. The last parameter for K sub G is E sub G, and that is the vertical distance from the center of the girder to the center of the deck. From the illustration, we have a girder, a small haunch, and the deck. E sub G is then half of 914 plus the haunch thickness of 25 millimeters, then half of the 300 mm thick deck, giving 632 millimeters. K sub G is then 1.5 times 2.122 times 10 raised to 10 plus 238,064.04 multiplied by the square of 632, and this gives 1.745 times 10 raised to 11. The distribution factor for moment is then computed from the equation, where for the spacing term, we take 2,500 upon 2,900 raised to 0.6, giving 0.915. From the space ratio term, use 2,500 over 20,500, then raise this by 0.2 to have 0.657. For the stiffness term, we use K of G that we just computed, then divide this by 20,500 or the bridge span times the cube of the deck thickness of 300, then raise to 0.1 to have 0.891. The distribution factor for the moment is then 0.075 plus the product of 0.915, 0.657, and 0.891, giving 0.611, or 61.1% of the lane moment is carried by each girder. Just to summarize, the final moment used for the design of interior girders is the solved raw moment multiplied by the distribution factor. Although the moment of the wearing surface is still the previously solved value of 231.14, and for DC, which is 1,239.21. The distribution factor is only used for live loads, so the moment due to live load is 61.1% of 2,203.51, which gives 1,346.34. This is for the interior girder. The distribution factor for shear is shorter and simpler. Using S of 2,500, we take the distribution factor as 0.2 plus 2,500 over 3,600, less the square of 2,500 divided by 10,700, giving 0.84 or 84%. The shear carried by each interior girder is then as summarized. From DW, the shear is still 45.1 kN. From DC, shear is still 241.8. And from live load, we take 84% of 468, simplified as 393.12 kN. Now that we have determined the raw shear and moment carried by a girder, we then place the factors from AASHTO LRFD. There are 4 limit states, where we can start with the strength limit state with the AASHTO table. Note that the factors for DW and DC are gamma p, which are found in another table as provided. Use the maximum factors, which are 1.5 for DW and 1.25 for DC. So the factored shear is 1.5 of DW plus 1.25 of DC and 1.75 of LL from the previous table, taking a conventional bridge, that is, strength 1. The factored shear for strength limit state is 1.5 of 45.1 plus 1.25 of 241.8 plus 1.75 of 393.12, and this gives 1,057.86 kilonewtons. The moment also follows the same factors of 1.5, 1.25, and 1.75. The factored moment is 1.5 of 231.14 plus 1.25 of 1,239.21 with 1.75 of 1,346.34, which yields 4,251.82 kilonewton meter. Use another AASHTO table for the service limit state, showing the factor of 1 for DC, DW, and LL for service limit 1. So we take 1 of 45.1 plus 1 times 241.8 plus 1 of the live load, and the summation provides 680.02 kilonewtons. Do the same with the moment, and add 1 of 231.14, 1,239.21, and 1,346.34, which results to 2,816.69 kilonewton meter. For fatigue, The factor to consider is only live load, so the shear is 1.5 of 393.12, giving 589.68 kilonewtons. The moment is also 1.5 of the raw moment, which is 1,346.34, and that gives 2,019.51 kilonewton meter. The last limit state is for extreme events, where gamma P is used for the dead loads, but gamma EQ is for live load. Gamma EQ ranges from 0 to 0.5, so to be conservative, we use the factor of 0.5. Thus, the factored shear for extreme event limit state is 1.5 of 45.1 plus 1.25 of 241.8 and 0.5 of 393.12. This is simplified as 566.46 kilonewtons. For the moment, we have 1.5 of 231.14 plus 1.25 of 1,239.21 and 0.5 of 1,346.34, giving 2,568.89 kilonewton meter. The shear and moment values used in designing the bridge relies on the different limit states.